I am the guy between you and the wine. Feels so powerful. So I'm the newest addition to UC Berkeley, fairly new. I joined here in January. UC Santa Barbara. I'm still in Berkeley. I came from Berkeley. I know. I spent a good 7.5 years in Berkeley. So it still comes in my, that's when I say that, right? So I'm going to talk about some cutting edge modeling tools that I employ to enable low carbon grids. To give a background of my research, I do almost the same things as Brian does. So I can skip some of that introduction. But I'm glad to be here. I'm glad to be speaking to a relatively smaller crowd. The first class that I inherited to teach, I have 140 students, and it's an elective. But it's probably the only class taught at UCSB called Renewable Energy, so everybody's interested in that. All right, with that, this is all new information. I'm just kidding. Everybody's talked about global climate change, our greenhouse gas emissions are going up, and essentially if we want to stay in this 2 degrees or 1.5 degrees path, we have to act now. So we all know this. Almost every presentation has said that, right? And of course, those have effects: wildfire, droughts, all these effects are going to affect our energy systems. What is also important, and Brian made this point, is that the current energy systems are also increasing water pollution and air pollution, especially in developing countries right now. So a lot of my presentation will move beyond California and the US, and also it's going to cover the global world. And one point that hasn't been made today is we should still remember about 1 billion people do not have access to electricity in this world. And I know somebody earlier made this point, I think it was Eric McFarland, that we should be talking about solutions where these solutions can be adopted by developing countries, that those populations don't have access to energy. They have to be affordable. They are aspiring towards a lifestyle that we have. So it'll be nice to sort of focus on those kind of solutions. All right, with that motivation, the exciting part is we have a lot of good technologies. LED technologies has transformed the energy efficiency paradigm here, right? Wind and solar costs are dropping really quickly. As a comparison, today's natural gas combined cycle turbine, which is the more prevalent technology here, is about $60 per megawatt hour. And this is just levelized, so we know there are challenges to variability and uncertainty of renewables, right? Electric vehicles, again, a big opportunity for cleaning up our air, but also helping decarbonize our whole transportation sector, if we do it right. And then finally, battery storage, those costs are coming down. So we have heard all these points through the presentations today. So largely speaking, and I know Gary covered that, so my presentation is like making all the points that everybody else did today, right? But Gary covered this, like 3 major approaches that are emerging for decarbonization. One is do a lot of energy efficiency, right? Reduce our energy consumption, deliver the same amount of energy services, decarbonize our electricity sector, and then use that decarbonized electricity to power our transportation. And that's why we need all the smart charging, so we can make use of that low carbon electricity. So this may be preaching to the choir, but thinking about the entire low carbon grid, the way I look at it, and many of us probably do that, is the original grid was designed to have dispatchable supply. We had our coal and natural gas plants, our hydro plants, and we had variable demand, right? And it's matching that. So we have to have supply equal to demand. Certainly we are seeing a lot of solar and wind on our power systems. We're seeing a lot of electrified transportation here. So it's adding to that variable mix. So it's make it more challenging to balance our supply and demand. And then to add to the mix, storage, hopefully the costs are going to come down, the life cycle emissions and impacts are also going to come down. But this is an exciting problem, that how do we balance all this, right? As Brian noted, we have a suite of options to go about meeting our goals. Which options should we choose from? And that is what I also work on. And then these elements are all spread out across the grid. And there's like hundreds of them, right? Hundreds, thousands. How do we plan for such a system? That's a pretty big challenge, and we need a lot of analysis from a system perspective, but also at like individual smaller systems. And of course, there are transmission constraints in all this grid. So I try to model our systems. So the modeling tools that I'm going to talk about today sort of cover, these modeling tools don't cover, of course, the entire gamut, but I want to situate where these modeling tools fit in this whole suite. So the first way of thinking about this is, okay, can we look at where wind and solar resources are? So that's the spatial planning of renewable energy when we think about how our future grid would look like. And that includes a lot of upstream modeling. It's called numerical weather modeling, where we have people who model the entire atmosphere. It's a big grid. We know where the wind is blowing, what radiation we are seeing for our solar systems. And then it come up with maps where we know where the best wind resources are, where the best solar resources are, right? And we sort of know, okay, where these are. So everybody has probably seen these maps from the National Renewable Energy Laboratory and some other private institutions as well. So we take that, and then we also look at how future demand will look like. Air conditioning loads is a pretty big deal here in California, as well as, say, countries like India and China. We're seeing more of these loads as our climate is changing, our temperatures are rising. But also electrified transportation, that's adding to a lot of load. How do we predict that? Like, we come up with these models. Now, Brian talked about one particular model that you use. There are other models that use agent-based modeling. There was a question about how to model this stuff, right? So we do that sort of modeling as well. And then you take both of these and then use those data to look at what is sort of the optimal generation and transmission investments that we need to make for a system so we can reliably meet our demand in the future. And then we take that and then look at how we can operate our system reliably. And that is something what we call system operations, or like these are unit commitment and economic dispatch models. And they basically simulate the electricity system to operate at the lowest cost. And the reason we simulate this is to look at different strategies on how should we operate this. How much storage do we need, and how do we operate that storage? Or should we change the technical limits on our generation plants? What would be the prices? What would be the cost of operating it? And then you compare these costs. So Brian showed the results. I'm just talking about the tools. And then finally, of course, there's the power flow and reliability analysis, which operates at different scales. So all these models, some of these look at yearly scales. Some of these are like 15 minutes or hourly models. And then these are like seconds or sub-second level. Now, my research is mainly on this part of the tools. Steady. That's what reliability analysis does. It's like transient analysis. OK. Now, the innovation that's happening in these sort of tools, especially in these two, is that we are trying to simulate the system, like building new investments in transmission and generation at the same time as dispatching the system. And that's because there's so much variability that is seen in wind and solar that we cannot isolate these two problems. And that is where the new innovations are in the last like 5 to 10 years. As an aside, the tools that we are developing are all open source. I want to make a plugin for open source tools. Some of the licenses for commercial tools cost almost like $50,000 to $100,000 for one license for 1 year. And that's a pretty big impediment for their adoption, especially in developing countries. And we feel that that shouldn't be what's stopping a lot of the developing regions to leapfrog to low carbon futures. So we're developing this couple of different platforms that I'm going to talk about. One is called MapRE for the spatial planning of renewable energy. And then for these sort of models, we're developing this model called GridPath, this modeling platform, which will also be open source. These are all like Python-based, using open source solvers or proprietary solvers, it doesn't matter. But it's really flexible, and it will help us to scale really quickly to develop region-wide models that planners and policymakers can adopt, change, so it's not a report that we give them, but actually empower them to do this analysis. All right, so with that, I'll give you two examples of these two different tools. So the first one about spatial planning of renewable energy, the challenge that we see is that we need to balance these trade-offs between siting renewable energy, and there are all these environmental, social, and economic objectives. So for example, this is a picture of a utility-scale solar plant. But it can be in the desert. There are environmental issues with that. We know we have probably read stories about displacing tortoises or other desert creatures. But there are sites that can be no regrets, as in places with low biodiversity losses, right? And that also helps project developers to not go in areas with high biodiversity value, because then there's less opposition to such particular projects. So we can scale quickly. For wind plants, this can cause deforestation, or they could be built in bird migration paths, again causing environmental conflicts. So can we identify the no-regret areas where we can install these plants? And then, of course, there's transmission, because we need to connect all these plants and then evacuate that energy. And that also causes land fragmentation, so we want to minimize those impacts. One example about how much land we might need for, say, meeting, let's say 100% renewable energy in California. Let's say 50% comes from solar, 50% from wind. The land that we might take is almost equal to the land area of Santa Barbara County. So that's a lot of land. But we also have that much land in, say, abandoned landmines or mining areas, contaminated lands in California, right? So we can exploit those particular sites. So it's a planning issue. And I'm not suggesting like we should do a top-down planning, right? We know, okay, Ranjit, you're not in India. It's not like a top-down approach. We have freedom of choice, but it's more about incentivizing project developers to go to certain areas by giving them transmission access. So here's an example that we did for 21 countries in Eastern and Southern Africa. So we do the spatial renewable resource assessment, looking at where the best, in this case, wind sites are. And then we develop what we call potential project areas or renewable energy zones. And this is a map of Kenya on the right, where the red areas are the best wind sites. Here's like Nairobi. And then we estimate a host of different criteria for each of these potential project areas. So the economic ones are levelized cost of energy for generation, for transmission, like how much would it cost to extend a transmission line to the nearest substation, right? Or how much would it cost to extend a road to the nearest road infrastructure? But we also estimate a host of non-economic criteria, like how close is it to a load center, or an environmental impact score for that potential project area. The capacity value, as in how well your wind profile matches your demand profile, because that would reduce the need for storage at the end of the day. We also have water availability, especially for solar plants. And then finally, co-location potential, where you can put solar panels in between your wind turbines. And this tool is like really flexible, where stakeholders can add their own variables that are important to them. You can use our tools to prioritize these areas by giving different weights to each of these criteria. And all these tools are open source. They're on our portal called MapRE, which stands for Multi-Criteria Analysis for Planning Renewable Energy. It's a Lawrence Berkeley lab website, which I still manage. And what this has done, like these tools, they have reduced the amount of time it takes to do such analyses. SMAP, which is the World Bank, the Electricity Sector Management Assistance Program, as well as the International Renewable Energy Agency, they have been doing such studies, but it took them almost like 1 to 2 years to complete like one country's analysis. And our tools have reduced that time to about 2 months. That just shows like the value of open source tools. Not to mention like millions of dollars, literally millions. Okay, so that's one example. The second one, I'm going to talk about like the planning and the systems operations tools. So we know renewable energy, wind and solar, they're variable in time because they're weather dependent, and they're also variable in space. You can't just put a wind plant anywhere you want. It depends on the resources, so they're spread across the region. So we want to extend transmission lines to connect them. And of course, they're uncertain, so there are forecast errors. I don't know exactly how much wind is going to blow 5 days from now, but I have a better idea 24 hours from now because of better weather models. So the challenge is, how do you plan and operate an increasingly variable and uncertain generation supply? So what we did was we are creating this modeling platform called GridPath. And this is an example of India's grid, a simplified one, of course, where imagine that we have all these like wind and solar plants all across the grid connected at different nodes, as well as conventional generation, and of course demand. And we simulate like the spatial model as well as a temporally explicit model. And we simulate it like either every 15 minutes of the whole year, or 1 hour, or whatever time frame it is. So the modeling platform is like super flexible. It's been applied to California, India, and South Africa, the example I'm going to show. But it's really easy to apply to any region of the world, right? So here's an example of South Africa. The study that we did was looking at South Africa's 2030 electricity system. And we were looking at, okay, what are the alternatives to this one dam that they were considering, or they're still considering, buying electricity from. And this dam is about 3,000, literally 3,000 kilometers from South Africa's border in the Democratic Republic of Congo. It's called the Inga Dam, and they already have 2 dams built there in the 70s and 60s. But the Inga site has the potential of almost 40,000 megawatts. Do you know how much is Three Gorges? 23,000. So this is almost double that potential. And people want to exploit that. So we did this analysis on looking at, okay, how much would it cost to build this dam? And are there any alternatives for South Africa? Can they get their electricity from somewhere else and how much would it cost compared to getting that electricity from this dam? What we found, and we did this optimization problem in GridPath and gave it all sorts of different options, right? So here, this particular graph shows what new capacity can South Africa build at least cost, okay? So this particular bar is the existing capacity, and this is what capacity it is, right? So let's not look at that for now. Let's just focus on the new capacity that the model built. And we did a host of different scenarios. So I'm just going to show you the main ones. So here, the green one is wind. The orange ones are natural gas, which is imported for South Africa, so it's a little bit more expensive. And the blue here is the capacity from Inga Dam. So these 3 particular bars are when we assume that the Inga Dam will be built and be supplying electricity to South Africa. And then this bar is where we said Inga 3 is not allowed to be built. Now the capacity for this bar is higher, but what was surprising in this particular analysis was no coal was built. If you know a little bit about South Africa has a lot of coal deposits. But even with the most optimistic cost assumptions for coal-fired power plant, it just doesn't make sense to build coal in South Africa, whether you build a dam or not. So that was a very surprising finding. And then I have a bunch of like different results, which I'll just share verbally, is that then we looked at costs. And in all of our scenarios, most of our scenarios, the scenarios which had just renewable energy and some amount of gas were less expensive than when Inga 3 dam was built. So Inga 3 hydropower is always touted as the lowest cost, but we are seeing even the basic economics without considering any externality costs. Renewable energy is now competent or competitive with hydropower and all these other conventional generation options. So that was South Africa. And then my last example of grid path, this is actually like a precursor to grid path, but we did this analysis for India. There are a couple of studies that came out that I was part of. One used a commercial software looking at India's future scenarios in 2022. So they're building 100,000 megawatts of solar and 60,000 megawatts of wind. And they're pretty much on track right now. They're building a lot. The amount of capacity that is going in India right now is comparable to the US capacities for renewable energy. And why are we looking at India? If you think about India's emissions growth, it's pretty much trying to follow China in a certain like really weird way. But India, in the last 4 years, increased its emissions equivalent to California's annual emissions. Does that make sense? India's growth in emissions in the last 4 years was the same as California's annual greenhouse gas emissions. That's a lot. So imagine every 4 years, we're adding a California. So it's super important.
They also have the worst pollution of any place on the globe.
Exactly. So there's a big incentive to convert the coal-fired power plants into renewable energy. So anyway, so we looked at this analysis for 2030, looking at optimal shares of wind and solar. And this is just one example that I'm going to give. So we did this host of different analysis, like how much would it cost, what new capacity would be built. But the final result was how does it affect the cost of emissions mitigation. That is our final metric. So I'll just walk you through this, and this is the last slide. So, yep, it's this last. Before wine, right? It's perfect. Rack up brains and then go for the wine. All right. So let's just focus on this particular part, right? So here, I had more animation in the PowerPoint, but then I converted it into PDF, and I have no animations here. So each of these bars are different shares of renewable energy, and it's just wind and solar. So from left, you see this wind turbine here. This is 100% wind, and then it goes to 25% solar, 75% wind, 50% solar, 50% wind, all the way to 100% solar. Okay, so going from wind to solar. And then these 5 are for 200 gigawatts of renewable energy. This is 400, this is 600 gigawatts. And this is roughly about 20 to 30% of renewable energy share to 30 to 40, and then 40 to 50%. So it's pretty significant, and it's a lot of capacity, right? And we wanted to see how much wind and solar they should be doing, because they have a very target-oriented approach. They say we have to do 100 gigs of solar by 2022, 60 gigs of wind by 2022, okay? So in all our scenarios, and this is just one, this base case, is that the 20%, the 25% solar and 75% wind scenarios were always the least cost in terms of cost of emissions mitigation. Notice that this is exactly the opposite of the targets that they have chosen to pursue, even with aggressive assumptions for solar cost reductions. And the main reason for that is because you have to curtail solar, is that duck curve. That duck curve, which is sort of it looks like a camel in India, for whatever reason, right, the way it's shaped. But we curtail a lot, at least based on this model. That's because the coal-fired power plants are not very flexible. Here in California, we use gas plants, which you can turn down much more, and then also have like these two shifting, as in you can shut down and then start up again. Coal plants, you can't do that. because these are all steam-based turbines. If you shut it down, you have to keep it down for like 24 hours or like it's very inflexible. So that's a pretty big reason to be wary about solar. We also did some simulations with battery storage and saw that only if battery storage costs between like $100 to $150 per kilowatt hour of like capacity, that's when it starts maybe making sense economically. But otherwise, every time you charge a battery and discharge it, you lose some energy because of efficiency losses. So it's very dependent on cost. And that's when solar maybe will get a little bit more competitive. But this is just a flavor of what kind of results we can get. And that would directly inform policy in a lot of these places. Our open source platforms would be hopefully released within the next 6 to 8 months. It'll have a user interface, and it's we're working with utilities and planners both in Southern Africa, 9 countries, as well as in India right now. We'll also be working with California, and some other regions are super interested. So hopefully it'll be an asset. But that's my last slide, and thanks for listening.
Snowy plovers.
Snowy plovers. Good one.